So yeah, big explosion. Okay.
Does they have their kill off and
Yeah, so this happens long before even the first microbes. But if the microbes, if there happened to be single cell organisms, they would all be eradicated. So we really want to think about that early moon forming event as essentially making the entire ocean into magma and not like fun, like bad magma. Okay. Yeah, like when you go to like Hawaii and you see like, oh, nice. That's like fun magma. No?
I'm sure. Yeah.
Okay. Any other questions? What's that? Yes, we have this one. I haven't made it yet.
Like the one from Thursday.
From this one?
Yeah.
Oh, I don't have any with me, but if you send me an email or a Slack message, I'll make a next one. Does anyone else need Kepler's third one?
Did you give that on Tuesday?
Yeah, I gave it on Tuesday and then I gave some more versions on Thursday. What's that?
The one from Thursday.
It's the same one.
Oh, it's the same one? Oh,
Yeah.
okay.
Okay. We could probably get started. Some folks will probably trickle in. So we tried to do the open house yesterday and obviously that didn't work. It's currently also not working because the sky has decided to put rain. So I think the rain doesn't really stop until tomorrow. So folks are asking, well, you're gonna do another one, but it's a ghost. Do you believe in ghosts?
Yeah.
Yeah, for sure. How many ghost believers are here? Okay, interesting. All right. So here's the open house that we were supposed to have. We have another one next week. So I'm not really going to reschedule it unless people are very adamant that they need one that's not on Thursday. We have another Monday one, just a little bit. Oops, let me scroll down. We have another Monday one here.
two left, right?
There's 3 total. So there's 2 Thursdays and 1 Monday.
Okay, what's left?
Of what's left, yeah.
Well, the 3 left then?
There's 3 left.
Okay.
Everyone okay? Okay. All right, so let's do let's talk about
Yeah, question.
What's the last name?
I mean, should we even end? I feel like we should just go forever. Right, just keep going, keep learning forever and ever. I don't know. It's the last day of finals.
Can we go to astrophys?
So sorry, the last day before finals. So there's like week 15. I'll pull it back up, but it's like the week after Thanksgiving, I think.
Because I have to let work on.
So we won't have any lecture during finals week. Do you normally have lecture in finals week? No, okay. So you have some time. What's that?
The week 15,
Yeah, I believe so.
the 29th of November.
Maybe. When is finals week?
Like the 3rd or 4th or something.
Okay. I thought it was a 6 or 9. I'm not gonna comment on this when I just had the thing up. I have to look at it because I'm real bad at dates. Only thing that I'm really bad at, like the worst, is names and dates. Okay. So we're gonna try and tie everything together. So we have learned all of these things. We're gonna put them into a pot in our head. And we're gonna try and like turn that pot into something that we can use. And then we'll use some examples to try to understand like planets outside of our solar system. And then rather than continuing to cram more material in there, like shove it in as hard as it'll go, I'm gonna let you choose what the topics you feel like you needed to learn, but you didn't. So not this week, so maybe like next Tuesday, I'll have you like write down 5 topics that you really want to learn about. And then I'll try and crowdsource them into like a couple lectures if we have time. Reasonable? So then the week before finals, that stuff won't be on the test.
It's in December, right?
I don't know. No idea.
It to the ninth.
Okay. You believe her? We'll
I
find
have
out.
it on my calendar.
Okay, all right. Is that okay with folks? Okay, any questions before we get started? Okay. We've had mixed results in the homework world. So we have SOTIs. And I think they go live today or they went live yesterday. So what I would appreciate is if you have had a positive or negative experience with any section of this class, that you tell me. Because if you hated this part, you love this part, you want more of this, you want less of this, I need them. I care about them. So it's your way of being like, look, I didn't want to say this to your face, because you're so intimidating and scary looking, but I really thought this, right? When I have a lot of people say that, I'm like, oh, look at this common thread that's coming out. Maybe we can change the way the course is taught. And I know that doesn't help you, but maybe it will help people in the future. Is that okay? Okay. What's happening here? 6. Good, that's correct. Is this a correct picture, like a photograph? Yes, vote for yes, no? Find it out. So what is fake about this? The color. Okay, what else? Those asteroids are huge. That's a very important thing to note, right? This is actually supposed to be a comet, but asteroids is perfectly fine. You can't see the tails good here. It's supposed to be like tails coming off, pointing away from the sun. And they're smashing into some gas giant. Anything else? What are the things you see? They're aligned. They're aligned like that? Yeah. Yeah. So they're in a line. They're probably getting broken up as they head towards this object. Any other fun things you see? This one looks bigger than that. Is that what you're saying? Yeah. So we don't know what the perspective is. So that's a warning sign. These two are very close to each other, right? That perspective is to be believed. You don't need the artist to be perfect. But is that sort of the typical distance that planets are at? No, so they're like small and far away. Right, okay, anything else? Yeah, there's lots of gas stuff circling around. We haven't really seen that before. So maybe we don't know intuitively if that's garbage yet. We'll keep that in mind when we look at planetary systems. Someone had a question about how does Jupiter have planets in a ring or in a line? And we'll come back to this idea of disks. We haven't really talked about disks. What are these? Comets. And they have two tails because one is plasma, the other is dust. And which colors are which here? So a lot of the things, just like generally speaking, you can kind of point them out here. Well, now you're an expert in planetary science, right? Yes. But one of the things you get to do, you take an astro class, and then you're like in college, and everyone knows you're the person who took astro that one time. So they ask you questions all the time. And then you like send them pictures. I have a friend who has breast cancer, and she woke me up today and she was like, send me things to make me happy. And I was like, you can do that. Every time you see something fun online, you're saved to your phone. You never know when you'll need it. Okay. All right. What's that? That's the moon, correct? What's that? So if the Earth were flat, okay, this would be the shadow during an eclipse. Is that what it looks like? No. Has anyone ever seen an actual eclipse in real life? Okay. What does it look like? Dark? Good. What's dark? Oh, you saw a solar eclipse. Okay, what about a lunar? The moon is completely dark and then looks kind of red. Ever seen that? No. Okay. So I saw this. This is from a astrophotographer that I really like. So he takes really high resolution pictures of the moon. The moon is full here or no? Slightly full, half full. It's not full. It is full? Why is it full? What's the relative position of, say, the Earth, the moon, and the sun? Let's say this is the moon. And we're the sun.
Lunar eclipse is when the Earth casts its shadow on the sun, or on the moon.
Okay, yeah, so if I'm hiding this from your vision, right, this would be a lunar eclipse. If I'm putting it in front of your vision, now I can't see you, it's what? Solar eclipse, good. And if you're in between me and the Earth, or sorry, me and the moon, you're the sun. Apocalypse. See how that works? Solar eclipse, lunar eclipse, apocalypse? Okay, all right, fine, I want to try it. Okay, so here on the left-hand side, you have the moon. The moon is moving to the right. Okay, it's actually physically moving, orbiting us. And it's moving into our shadow and out of it. Okay, so sometimes you'll see the eclipse start. Okay, and you'll see it looks like a curve. Because the Earth is round, good. Okay. Or at least a circle, flat disk, right? At least we know that. And then at this point, it becomes super red and then it heads back out again. So these are called partial eclipses. This is a full eclipse. Anything else you notice about this picture? What's bigger, the moon or the Earth's shadow? Yeah, the shadow of the Earth is massive. Right? And this is a picture that I really enjoy when you get in a lunar eclipse. You don't really get it very often, is that you can see this entire shape of the shadow is moving through the shadow. So at this point, it's just deepest in the shadow. Now, why is it red? Just like I thought, spooky season was over. It's witches magic, blood magic. Hands up, yeah, blood magic. Got a blood magic in the back. Why is it red? The sun, yeah, so the sun is illuminating it. Wait, you just said it was shadow. No, right. Yeah.
Doesn't have any, like, infrared light, the light that we have on.
Okay, I like that as a potential explanation, but we can't see infrared. So that won't work here. Yeah. Mm-hmm. Okay. Okay. I like that, but not as much, because if we could see through the Earth, that would be a problem. So you can do that because you're mostly water. You can see through like very thin, like membranes, mostly water. This one's a little less intuitive. Okay. Now you have to imagine this is Earth. Okay, if you stand here, this is noon. And let's say you're all the sun, so this is pointed towards you. The sky is blue and the sun is white, right? Light's coming in, going right to your eye. If I stand here though, that's no longer the case on either side. What is the sky at sunset? Red. Why is that?
Even though the blue light is
Yeah, blue light really likes to scatter. That's what makes it blue while we're standing at noon. So blue light scatters and red light just keeps going, lives its own life. When you're over here, blue light gets scattered, you're left with no more light, and then you only have red light left. That's what you see. What happens to that red light after this point here? I'm standing on the edge of the Earth. Okay, light's coming in my eye. Let's say I'm not standing there to take it in. Where does it go? Light goes here. Does it just stop arbitrarily? No, it just keeps going. Okay. So light can actually go around the Earth, curves a little, bends just like a prism,
Right.
and the only color that's left already is red. And so this is the Earth's atmosphere illuminating the moon. It's like a sunset or sunrise projected on the moon. That's like, I think that's really cool. This only becomes this beautiful, this red, this important, when all of the rest of the light is extinguished. So when you have a partial eclipse, you don't really see it. Because it's so bright here and it's white. You have to wait for all of the light to be totally extinguished. And then you get this focusing effect when you're directly behind the Earth. The whole atmosphere bends light towards the moon. That's it. Okay. Questions, comments, concerns? So now you can explain that to all your friends what you didn't see last night. Okay. All right. So we are let's just do a quick recap on impact cratering. We talked about that in the context of collisions. So we've seen a lot of these little impact cratering telling us like how old stuff is getting hit. We're gonna come back to this word, period of heavy bombardment. But we also wanted to talk about it in the context of like big stuff hitting each other. Okay. We particularly wanted to think about maybe this explains some weirdo stuff that we've seen around the solar system, stuff that like didn't really add up. We said I'll explain it later. So I said maybe it explains the fact that Uranus is like tilted. The Uranus got into a fight, right, and stumbled home on its side. Maybe explains why Venus. Have I told you the Venus hypothesis? Favorite unprovable hypothesis. I got time. Okay. So very well-renowned scientist, planetary scientist, goes to a conference and he says, I have a theory for why Venus is basically spinning the other way and very slowly. He says, I cannot prove it. In fact, it's basically unprovable. Okay, so here's the theory. Venus, similar to us, gets hit very early on. And we saw with our moon that the fact that we got hit from the side changed our rotation and even changed the way that we were tilted. And then we have a moon that rotates in exactly the same plane as the orbit of our rotation. Okay. So these are going around each other, all is beautiful, all is well. So imagine that happened with Venus. What you haven't learned necessarily is that the moon is moving. The moon is moving away from us. Okay. And if it were orbiting in the other direction, it would be moving towards us. It takes a while, about 2 centimeters or 2 millimeters per year, I think. A really, really small amount. You're not going to notice it in your lifetime. But over the course of like all of history, that would be a significant distance, right? Okay. So he says, what if you form one moon? It's going around, everything's fine. And then you form another moon, smack it again, but this one is going in the opposite direction. Now, all of these things, one moon's going to be pulled in, and then it's going to hit the other one on its way in, but they're going to smash into each other, and then they're going to fall into the surface. And all of the evidence of them will now be inside of Venus.
Huh.
And of course, Venus is hot. Everything melts. Whole surface gets removed every 600 million years. So you have no evidence. And he said, I will never publish this paper because it's untestable by definition. You can't prove it. But it kind of makes sense. Okay. So this is this place that we're going to get to in our theories. You say, what if I just hit something? Maybe that explains why it doesn't work. Okay, so we're going to have to adapt some of our theories. We're going to do that with some weirdo things. Okay, like why does this potentially rotate backwards? A lot of people think maybe it was hit. Okay. This is how you get Pluto and Charon. Pluto and Charon very similar in mass. They're orbiting each other. They have a lot of little leftover pieces. Maybe they're even leftover from the collision itself. And then you have Mercury's large core. We talked about this a little bit earlier today. You smash the top of Mercury. Let's say it has like half core, half mantle. You just break off the exterior. That exterior, whatever moon that you were going to create, it really sees the sun, likes the sun more. And so it might go hang out with the sun. Okay. It's okay. Questions? Okay. So let's think about all of the things we've learned. We've got 8 planets. They all lie in the same orbital disk. We have one that doesn't. Planet, that's Pluto, so we kicked him out. Doesn't make sense for a theory, you're not part of us anymore. Okay. Some moon systems do the same thing. Someone already pointed this out. Jupiter has planets that lie in a plane. They even lie in the same plane that we are in. That's pretty weird. We found that there's 2 types of planets, and they're different. What are the 2 types of planets? Sorry, say that again?
Terrestrial and human.
Terrestrial and Jovian. Okay, terrestrial looks like Rocky, Gus, you stand on it? Jovian? Yes, you fall forever and you get crushed. Until liquid hydrogen. Yummy. Okay, they're separated from one another. How are they ordered? Which comes first when in relation to the sun? First rocky, and then gaseous. If you saw gaseous in front of rocky, would you be surprised? You don't know yet. You don't know how the solar system was formed, right? So what we know so far, we only have one solar system. It's the best one. Everyone likes it, right? Okay. We found 2 types of small bodies. What were they? Asteroids, good. Rocky, right? And comets, were those gassy? Icy, good, okay, I like that, right? So you got gassy, icy, that's like far away. You got like rocky, close. Okay. And then there are exceptions. Because no rules are good and everything's complicated, right? Am I missing anything? Okay. Let's talk about the formation of the solar system. We need to describe all of these things more or less in a theory that's self-consistent with all of the evidence that we're presenting. Okay. We have to explain something called orderly motions. Everything is happening in a flat plane. Why not randomly? We need to explain 2 types of planets. We need to explain their composition. We need to explain where they live. Some live close, some live far. We need to explain 2 kinds of body, why they're separated. Why don't you have a ton of icy stuff where the rocks are? Why don't you have a bunch of rocks where the ice is? And we have to explain the exceptions, right? Now for this section, we will be using new forms of evidence. Stuff that you haven't seen before necessarily on the left here, and then the stuff that you have seen on the right. Sorry, in the middle, and we'll use that to interpret this stuff on the right. Star forming regions. This is going to be the pretty pictures part of class. And this is going to be a little bit of me telling you what it is, and you being like, okay. Because I can't necessarily present you with the spectral evidence to show you. So like, we could after class, but you won't like it, it's boring. Okay. Looking at the formation of the sun, you'd be like, okay, that's the best place to start to understand the solar system, right? How would you do this? How could you possibly learn? Let's take a step back. How can you possibly learn how a star is formed? Right? And we have a time machine. No one has a time machine? Someone just won $2.04 billion. And I'd love to know what those numbers were. We don't have a time machine. Okay, what could we do? Right? And that's a thought. Might get divine revelation. So if I look around this room, I see a variety of students at different ages. Okay. And I look at the group of students and I say, okay, there are similarities and there are differences. And I could potentially guess how old some large fraction of you were, right? Because I could determine rules about what aging does. Okay. So this wouldn't be very good because there are no kids in here, and I would have a huge bias, right? So I would need to also include, there's a daycare across the street, and I need to watch all of those groups to figure out how something small gets big, right? Okay. So we can't watch our son grow up. our lifetimes are tiny compared to the billions of years that we'll live. But we can watch other suns. And we can look around and we see all these different stars. We try and piece together a story about what we're seeing, especially with young stars. So we can go look stars that have just been born in a cosmic sense, not for us, obviously, but we can look around them. You can see what is around them. Are there groups that look like toddlers? Are there groups that look like infants? Are there groups that look like teenagers and knowing their parents? Not really, it's a joke. Okay. So that's what we're going to do. We're going to observe many stars of many different ages. Okay. I'm going to start with my favorite type of word, which is just like a Latin word for stuff that they didn't know. So that's the word nebula. It means mist. And mist is just when they looked up in the sky and they saw just like stuff, fuzziness. They didn't know what it was. They called all these things mist. So some nebula are galaxies, great naming choices. Some of them are the death of stars, and some of them are the birth of stars. Okay. For the purposes of what we're going to talk about, we're going to try and only talk about these clouds that are going to make stars. Okay.
We're talking about the mass of the moon, the mass of the stars.
We're not going to talk about stars at all.
Okay.
That's a whole nother class. Stars and galaxies
Okay.
is the next one in the series. So you can have 15 weeks of talking about stars. Boring. I'm just kidding, they're cool. Okay. So this is if you've ever seen Orion, Orion's the one that, you know, has a little arm and he's got a belt, Orion's belt, Men in Black, Orion's belt. Okay. So this here is a star forming region in the trapezium cluster. And this is called Orion's Nebula. On the left is the visible. So visible is really good at seeing dust, even in space. So it's really dusty on the right-hand side. And infrared, you can sometimes see through the dust. So we can use multiple versions of light to be able to get a better picture here. And so you see a whole bunch of dust, then you see some really bright stars. And stars tend to be really bright right when they're born. They're just like really violent and explosive. And in fact, they're very blue. You could talk about that if you wanted to. Blue means that they're hot, just like iron pokers. Same thing's true of stars. Same rules apply. Okay. So this is a fun, well, I guess we should turn this off and have people go to sleep, right? Because those are just all nebula pictures. That's too bad. Okay. Anyone want to fall asleep? Raise your hand and fall asleep. Got one. So we're going to see lots of details in here, and the structure that you see here is real. So for example, you see this like dark piece that's going across on the bottom. That's a real like sort of crust, if you want to think about it. A lot of these structures that you're seeing, they're filamentary structures. The scales here are really, really difficult to conceptualize. Keep in mind, that's not like a bunch of planets all sitting next to each other. These are like thousands of light years between them. Okay. So all of this gas is really, really thin and really spread apart, but I'm viewing it from so far away that it looks all squished together. Does that make sense? Okay. On the left-hand side, you have Hubble. Hubble sees in the visible, and you have some nebular matter, and then here you see JDST. It says color, but what we mean by that is that it's been colored from infrared so that we can see it. And you can see through the gas and dust again. So here, for example, you have some stars. They're really red. They get scattered light. And here, they're very bright. They're brand new. They're doing some fun stuff in here that we're about to investigate. So you can pick this thing apart. You can see that there's a young star. It's just forming, baby star. And he's heating up his cocoon like he's a little spider. That has lights on him for some reason. And then you can see that here. Oh, that's what it says. Okay, good. So you have this little disk, okay? And there's this cocoon of gas, and we're going to get a better picture of that in a few seconds. But here's the important part. This is the orbit of Neptune, right? So that's the scales that we're thinking about here. We bring that picture, the orbit of Neptune, down into this, and then we compare it to these, right? To massive, massive scales. And all of this filamentary structure is real. Kind of cool, right? Yeah, okay. What's this? Pillars of Creation, good, is a very famous image. It's also by a Hubble Space Telescope. And why do they call it Pillars of Creation? Stars are being formed here. Stars are being created here out of gas and dust. This stuff here will make stars. So here's one that was made, and they're in the process. Yeah.
So, because it's creating stars, does the sun create about that?
Very good question. That's correct. The sun was created from gas and dust. And we'll show exactly what kind of gas and dust. Okay. And if you're thinking to yourself, well, wait a second, there was just gas and dust. How was the earth made? That's the right next question. Okay. So let's go back and forth between this one and the next one. So this is Pillars of Creation. When you see different pictures like this and you're like, oh, that's not real, they changed the colors. That's okay, right? We just like slide things over, we use a filter, we do on Instagram, it's the same. Okay, so on the left-hand side, you have the visible. And this is how we would see it if we had telescope eyes that were the size of Hubble. We don't. And then this on the right-hand side is what it looks like in the infrared. And again, I told you that sometimes in the infrared, you can see through dust. And so I want you to try and draw your attention to some similarities here and then some differences. So for example, here you see these little dots. You don't really show up here. There's way more stars on the right-hand side than there are on the left-hand side. This big bright one, probably this big bright one, but there's like a missing star in here. All of these stars that aren't seen because the dust is absorbing that light. And then if you look down in here, all of this gas and dust is, you see all of these ones. They're just becoming illuminated. They live inside this gas and dust and they're being born. And let's see if we see any of the ones that are important and fun. Oh yeah, there's one that's like right in here. It's like just baby born. Okay. Here's another way of talking about that same piece. We're zoomed way in now. And this again is in the visible. So just looks like a, I don't know, something from Star Wars, like an elephant or something. Okay. And then when we look in the infrared, we can see through it. Isn't that cool? So if I flick between these, you can see some of the same structures, like this thing here. You see that? And then you see, oh, this is the star that's forming from this collapsing gas cloud. Isn't that kind of cool? Okay, so gas and dust are collapsing, they're making stars. Yeah.
Is it lightning then?
Like this?
Yeah.
No, these are just like concentration of gas. But good question. Yeah.
Since the stars are being formed by the gas and the dust, I feel like this sounds kind of stupid, but does the gas and the dust ever like run out?
Good question. Okay, not a stupid question. No such thing as a stupid question. So, okay, let's go back 1 second. We imagine that's all gas and dust, right? It's all gonna fall in and make a star. Does that mean that like every star like eats up the whole cloud? You don't need to have an instinct about this. No. So it doesn't eat up the whole cloud. So what does happen? I'm gonna actually, this one's funny. We're gonna go one more. We're gonna look at this one. This is a direct answer to the question. What's going on here? I mean, other than this looks like a fucking painting. This is beautiful. It's not a painting, it's a real picture. Okay, where's the empty area? Here? Yeah. So this one's another spooky one, right? Okay, so this looks like there's an empty area.
There's also like a cluster of stars.
Here? Yeah, it looks like there's some stars in here. I can't really tell perspective there, so I can't tell what's close or far. Maybe these are in the foreground, maybe they're not, but they're really blue. Yeah,
So what stands out, I guess, is the fact that it looks like it's pushed away. Like the area that's empty has it, they're gonna like push away from that emptiness.
so this is what I wanted to point out. So as these stars in here that were just formed, they start to get hot. They get hotter and hotter and hotter, and they start basically spewing out light, but also they start blowing out solar wind that we talked about before. Very hot electrons and protons come streaming off the surface, and they start smashing into any gas that's left over, and that stops the growth. It pushes, this is all gas and dust, literally being pushed away by the brand new stars. So stars have a very limited amount of time to eat up as much as they can, and then they're done. Okay? And that's the same thing you can see right here. A brand new star pushing out all of the gas that it was created with. Make sense? When you see a picture like this, it's very tempting to think that like at the very center, you know how it looks like there's this beautiful cross and like it looks like maybe there's a sphere in the middle. You're not seeing the surface. Every star that you've seen in a picture like this is never actually bigger than a single pixel. We cannot see any other surface of any other star in any other solar system in the whole universe. We can only see our sun because it's so close to us. So this is an illusion created by how the telescope bends light. It takes more than one pixel. Okay. But if you're looking for a planetary system there, if you're using your eyes to look very closely, you have to look so much closer. Okay. So if it has a planetary system, it's all within that dot. Does that make sense? Okay. So now you're experts on nebular collapse. Cool. Okay. Sorry, that's bad. I should have warned that. So where did the elements in the solar nebula come from? So we say nebula, that just means like cloud. And solar, that means us, sun. I'll use the word sun and us interchangeably. I recognize that we don't live on the sun. And then you have this body here that we're going to talk about in detail. Where do all elements come from? Anyone know?
Hydrogen, helium.
Yeah, hydrogen and helium. And that came from Big Bang. Whole show about it. That's what it's dedicated to, right? Did I just explain that from the beginning? Yeah, for 15 seasons. So we start basically with this hydrogen, and this is helium. Helium makes your voice funny. Hydrogen is flammable, extremely flammable. Okay, put too much hydrogen in a room will explode. Okay, so they're kind of funny because on this side, it's like, you know, water and everything that's fun and explosive. And on this side, it's just like, I don't want to participate in chemistry all the way down. So if you're a chemist, you're a nuclear physicist, you stare at this for a long time. All of this stuff is like weirdo stuff. Like you just don't find it in your day-to-day. The biggest one over here, radon, you will find in some basements. A health hazard naturally comes from the earth. It's radioactive, can give you lung cancer if you don't pump it out of your basement. But you don't have to worry about that because almost everyone does. This stuff is heavy down here. This stuff is light up here. It's separated for a chemist to figure out, not for you to figure out. You don't have to worry about that. This will not be on the test, except for the fact that hydrogen is up here, helium's over here. You have stuff like lithium, beryllium, all of these elements. They're all created from just this one and that one. It's smushing them together. Okay. Okay. So right after the Big Bang, this was the astronomer's periodic table. Pretty straightforward, easy to remember. That's not that simple, right? It's just two. Big H small he. Okay, mostly hydrogen, some helium. Want a fun story about helium? Why is it called helium? Does helia mean helios? Sun. Helium was not found on Earth. The first time we ever found helium, we found it first in the sun. Because helium doesn't like to participate in chemistry. It's really light. So it doesn't get turned into any molecules. It's not in our body. Well, kind of, it's in our body, not really on purpose. And it ends up just like sitting in the atmosphere. And if you don't make more of it, it just sits in the atmosphere, kind of moves to the top, and it just like disappears. But we didn't find any of it. We found it later, once we knew what it already was. We first discovered hydrogen right here. It's everywhere. In water, hydrogen, oxygen, right? Helium doesn't participate in any of that chemistry. It's called helios. Fun story, bad story. Fun story. One person. Okay. So most of the universe right after the Big Bang was hydrogen and helium. In fact, it was probably all hydrogen, and then right in the Big Bang is when you make the first helium. And you do that just by taking a proton and a proton. You're gonna be best friends. And they say, we don't want to be best friends. They try and push each other apart because they're both positive. But they're like, no, you're gonna be best friends. And then one of them says, well, I'm gonna be a neutron. He just slide. And then now you understand how stars are made. Okay. So this is essentially what happens. You first start with hydrogen and helium. The very first stars that are ever created, they only have access to those two. And they try and squish at the very, very center, where the gravity is the largest. Hydrogen presses into hydrogen, makes helium. Helium presses into other stuff, makes beryllium, makes carbon, makes oxygen, makes nitrogen. That's all in the middle. How does it get from the middle out to where we are?
Someone else had to put energy into it to make it.
Yeah, almost there. You have to get it out from the inside, right? You gotta kill the star. Star has to die. So you might have heard things like, oh, cosmically, we're all stardust. This is what we mean. The interior, the exterior of our body, the skin, is created from the interior of stars that have died. Yeah. So up here, you have all that gas and dust. You're like, well, where'd that come from? That came from dead stars. Okay. So then it gets recycled. And it's basically this really wonderful reduce, reuse, recycle. Except are you reducing? You're not really reducing, you're creating more stuff. I don't know. The net amount of mass is conserved, but it changes forms. So you're making more heavy stuff each time that you burn it. Okay. So today you have this, and this is sort of like how astronomers look at the world. They do this really annoying thing where they say anything above this line, okay, hydrogen and helium, anything below it is a metal. They call it metal, not metals. They just like to mess with people. Okay, so magnesium, bones are made of that. Carbon, nitrogen, oxygen, those are important for life. Neon, that's important for lighting signs. Silicone, wait, did I do this on? What's S? Sulfur. Good. Argon, iron. So all of these are in your body, making up all the important pieces of you. And they constitute a tiny, tiny, tiny fraction of all of the elements. So a majority of the universe is in fact hydrogen when you're talking about matter. Okay, super boring. That's why I said those pictures that were just gas and dust. The stuff inside there is just mostly hydrogen. Okay. So what would the astronomer's periodic table look like? We looked at the universe in 13 billion years. Would A, it look exactly the same? B, the H would be a little smaller, but not much. Other elements a little bigger. C, the H and E would pretty much all be gone, converted to heavier elements. Or D, all the elements would be the same size, that is the same amount of everything. Let me know when you're ready to vote. Okay, let's vote on 3, 2, 1. Okay. No one liked 1. We don't have to argue for that. I'm gonna turn to your neighbor and ask them what their answer was, see if you can convince them of yours. If you don't have a neighbor, you can turn around or tap someone in front of you. Trying to be friends? Yeah, let's try a revote. Let me know when you're ready to vote with your fist. Ready to vote? Okay, let's vote on 3, 2, 1. Okay, all right. You don't want to defend their answer? Let's go back really quick, okay? This is what it looks like now. What did it look like 13 million years ago? Only hydrogen and helium. Okay. Yeah,
We depending on.
sure. If you want to.
I just said B is. If our universe right now is 13 million, to go ahead and see what elements are left and for hydrogen would get a little smaller. But considering it composes mostly everything, I don't think it would get too small.
Okay. We will agree with that. So no one liked this one. What about getting rid of it all? You don't think that we're like using up the resources too quickly? We made it this far. That's a good point though, right? We made it this far 13 billion years. How much of the stuff did we end up using? 2%? In 13 million years?
So if you want to go another, it's like, what change?
Yeah, okay, good. So this is a great way to think it through, right? So maybe H will be maybe 2% smaller. That's a tiny change. If I got a 2% raise, I would not be happy, right? You got a 2% tip, you would not be happy. It's too small. Okay, and then this one's obviously garbage. So this is garbage, and it's B. Okay. So this is what it looks like. There's actually a bit more helium. Hydrogen turns into helium, and helium turns into everything else. But it's still mostly hydrogen. Slightly less liquid. Okay. We need to really quickly remember conservation laws before we can talk about disks and how we form all these things. Conservation laws are not like what people in front of Walmart are trying to get you to do. right? You're not conserving, it's not Greenpeace. Conservation laws is this really dorky example. It's called Newton's cradle. Got a bunch of balls. You suspend them by a string. You pull one of them back, you let go, and it makes the other one go. And it comes back, hits this one, makes this one go. Have you seen this before? Okay. If you haven't played with them, they're really fun. You can do like 3, pull 3 back, and it makes 3 go. All right, I'll bring one on Thursday. We'll just play with it all day. Okay. So how does an ice skater spin? How does a rollerblader spin?
You pull the arms.
Pull the arms. And everyone intuitively knows this, right? Because we're all really good at ice skating. Or like if you're dancing, you like do a little pirouette, gotta go fast, put your arms in. Okay. Where does energy come from? Do not say the gas company. What's that? I said, the soul. It's not that bad though, right? So it is in fact from one solar company called the sun. So almost all energy on the earth comes from the sun. So for example, you ate a burger today or whatever, some fries. The potatoes were grown with sunlight. The oil was created with stuff that either ate the stuff that made sunlight or itself was like grass. Right? So almost all biological things get their light, their energy from the sun. And even when you have solar panels, you're taking that directly. So this gets into this idea of where does energy first come from? Can it be lost and can it be created? This is your biggest, like, if you want to get scammed or you want to scam someone, tell them that you can give them unlimited free energy. Right? For just a small upfront cost of $10 billion. Okay. This is impossible because all energy has to come from someone. And it all goes to someone. Okay, so this is the uncomfortable thing about calories. Okay. So you eat food and then you gain weight. Shit. So what happens here? It's a math equation essentially. You got to eat food that equals how much you burn. Otherwise, it accumulates. Right? Now, that's obviously a reduction of all nutritional science. Don't tell anyone in the department I said that. But my point is that energy is what you're consuming with food. Right? Where does your mass go, by the way? Let's say you're working out. Anyone notice anything? How do you lose weight? Yeah.
Oh, wait, what's the question?
How do you lose weight? What process? People are gonna say pooping, and that's not it. What's that? Yeah, when you're exercising. Let's say you're exercising, you lose weight. Where did it go? Respiration. So you literally grab oxygen out of the air and you breathe out carbon dioxide. So you take the oxygen from the air that you use in your body, and then you put out something heavier. That's a net difference in mass. Okay? Mass is never created, it's just converted. Energy is never created, it's just converted. Fun or stupid? Okay. Both fun and stupid. Okay, good. So we're going to use this in a context that we're going to understand in a few seconds. So first, we need to understand this concept really well. Then we're going to use this concept. It's going to make a lot of sense, and then we're going to be able to understand the formation of the solar system. Okay. Conservation of angular momentum. It's a weird way of writing this. The mass, the velocity, and the distance from the center or the radius. Okay. This product, when you multiply all of them together, it's a constant. Okay, so in practice, what does this mean? This means that if I'm starting like this, and I'm rotating rather slowly, and I pull my arms in, I should rotate faster. Why is that? My total mass has not changed. So I can ignore this part. What has changed is that my radius, maybe is half or a third. So if this goes down, radius goes down, velocity has to go up to compensate. Okay. Okay, so we're going to use this intuitive concept to describe the solar system, I promise you. Did I just say that? I kind of gave up on that. We can try it. Let's get a freebie in. Okay, the freebie in the bag. If angular momentum m times v times r is conserved, what happens if r goes down with no change in m? Let me know when you're ready. Let's vote on 3, 2, 1. Oh, I got some people changing. All right. All right. Who wants to argue for their point here?
Because the radius goes up, velocity has to compensate.
Okay, so let's work through that. So m isn't changed. R gets small. And so V has to get big. People agree? Okay. Maybe this ends up on the test, we'll find out. Copy and paste. I like to do that. Okay, so that's the whole picture. Now find it intuitive. You spin fast, slow down. Fast, slow down. Okay. Okay. Here's conservation of energy. It's just moving between different types. In general, we like to talk about it in the context of kinetic energy, stuff that's moving, and potential, which is the ability for something to be stored and used later. So for example, during the day, we pump water up a hill. That's because we have stuff that's making electricity. And that's happening all the time, but people don't use it all the time. So what you do when people aren't using your energy, so you pump water up a hill. And then when they need more energy, you just let it come back down again. So you put, say, for example, something heavy up a hill. And as it comes back down, you can get the energy. Take a giant battery that's made of water. Okay. So that same thing is true here. You've stored in some form here. This person is putting energy to get moving, right? You want to move up the hill. There's two forms of energy here. Going to be at the top. You want to fall back down towards the bottom. And you're moving. So movement itself is a type of energy. And we're going to add that to the fact that you're on the top of a hill. And you can be released to go back down. Makes sense. Where is the speed the highest? Up here or down here? At the bottom. Assuming that you're bicycling the same, like you're doing the same speed, and then you just let the hill take you down. Okay. If you're down here, and of course you've been in this actual position before, like I'm not moving fast at the bottom of the hill, especially when I go up. Like that's a lie. Why am I lying? I'm not exactly lying. I'm oversimplifying. Here, you're moving slowly because you haven't stored up the potential energy yet. Once you saved it, then you can use it. And you can choose not to pedal anymore. Okay. Another way of thinking about it is, let's say it's a really big bike ride. I'm like eating Snickers bars as I go. Those are energy. So the net energy is going into me going up the hill. Okay. Kinetic energy, potential energy, energy. Okay. There's no magic here. We talked about this one, I think, before. It's never created or lost overall, just transferred between forms. Cross makes sense. I'm gonna like skip through the rest and talk about how we use it. This becomes heat. This one's important. This is called friction welding. It's really cool. You just spin something and you have it touch. The fact that it's spinning so fast melts it, including metal. This is taking waves. This is taking the motion of waves, forcing a turbine to run. So you can take kinetic energy and turn it into potential energy that you use later to watch YouTube on. Okay. Okay. So these are the two things we have to remember. They're conserved. You do not create them. You cannot lose them. Opposite of your keys. Okay. Angular momentum and energy. So let's talk about this in the context of a solar system. You got a big old ball of gas. Huge ball of gas. Okay. How does it become this? So we start with this idea called nebular collapse. Nebular collapse. Okay. You had all this gas, and some of it started to get closer. And the places where it's closer pull other places by gravity. And that's a runaway process. Because if I add more mass, then the gravity gets stronger, right? You keep adding mass, keeps pulling more stuff in. Right? Okay. So sure enough, we start with something that used to be sort of uniform in size. And as it gets smaller, gravity in the center increases and it pulls in faster. Okay? And let's look through all of the repercussions of that, knowing what we know from before. So, as the solar nebula collapses, it spins faster, it heats up, and it flattens out into a dome. Okay, so why does it spin faster?
The radius.
The radius gets smaller, and just like our ice skater, you speed up because you're being pulled together. You might be thinking to yourself, how is it spinning at all? It's just gas. Perfectly good question, right? Well, everything's technically spinning with respect to a specific point. I am currently spinning around this room. You are also spinning around me, right? If I'm in motion, I can always find a reference point to be like, okay, I'm spinning around that point, right? All of these little pieces of gas, they're just living their daily lives. They don't really see any spin at all. And yet, as they start to come closer, their spins are going to increase, they're going to start moving faster, and they're going to end up with these massive spinning motions. Okay? Why does it spin faster? We just talked about that. Why does it heat up? Yeah. Okay, because it's spinning. So we're thinking about like rotational motion that has energy in it too. That's not wrong, but there's another reason too. Yeah.
The conservation energy.
Okay, conservation of energy. So what does that mean?
So it's like, as it's getting, smaller, it's converted into kinetic energy, and so it's like, and it's also getting further as well.
Yeah, so we have a whole bunch of words there that we need to dissect. Let's make a picture. I'm really bad at imagining these things, even though I just asked you to do it yourself. Okay. So there's your gas cloud. Your gas cloud consists of individual atoms. You can't see them, they're here. Okay, you can name them if you want. And they're just hanging out. They're just going whatever direction, doesn't matter. And as the cloud starts to collapse, gets smaller, the total volume is going to decrease, and their speeds are going to increase. So why do their speeds increase? It's like playing pool, but in space. Okay, so every time that one of these bounces off the other one, just like a pool table, one's going along, gets hit, then this one goes off in another direction. You hit it really hard, the other one goes really hard, right? So that's all happening in here, except everyone's bumping into everyone all the time. Okay? And if they get closer, those hits become more violent. We already started spinning faster. You're getting closer, speeding up. And all of that results in the entire gas getting hotter. The idea of heat is just the individual atoms bumping around. Make sense? Okay. Why is it flattening out into a disk? This one's the hardest one. This one, no one can guess. I want you to try. Wrong answers are fine. Okay. Something to do with gravity. I like it, nice and vague. Is it like like if I'm spinning a pizza? Is that what this is? So a lot of people will go to the answer because that's sort of like this intuitive answer, but it doesn't quite make sense because pizza is like made of dough, it's stretchy. Right? That's not really what we're looking at. Definitely has something to do with gravity. What's that? Close it what? Oh, like gravity's pulling at the edge to act like the sticky dough? I kind of like that. That's not quite it though. Great thoughts though. So some people say it pulls the material into a disc. Well, what do we mean by that? So like if you start with a ball, then it like flattens out in one direction, just like pulls along this direction. But if you thought about that for a second, and you say, well, wait a second, then why aren't the planets flat discs? You say, well, they are, and we had that conversation. Or that it's being flung out like pizza. And that's not it either. Let me show you why. It's really, really counterintuitive. Okay? So it's gravity's pulling everything spherically, right? Gravity will be at play here, but I'll show you how it's slightly different. The gas particles, okay, they're on individual orbits. They're floating around, just like the comets were, around whatever's in the center. Okay. They're not getting flung out. They're not feeling any of the results that a pizza would. When you spin a pizza, and it gets moved away. All this stuff is falling constantly towards the center. Okay. So here's what happens. As the nebula collapses, clumps of gas smash into each other. So you start with everyone, like imagine, we're not going to do this, but imagine you all stood up and you all just started randomly walking around, okay? Bumping into people. Okay. If you're random, if I'm walking this way, you're all walking this way, I keep bumping into you, what'll happen? You'll eventually maybe want to start walking this way, so I stop hitting you, right? And then maybe all these people who are walking around this room very slowly, they choose a preferred direction. Hitting each other is not as fun as not hitting each other. Okay, so that gives you that rotation that we saw before. It's a preferred direction. The direction that all of the gas ends up either smashing into each other and staying in that direction, or already was going that way, very lucky, doesn't get hit for its whole life. Probably still does, but okay. And then let's say you live, so everyone's in this preferred disk direction. Let's say you live on this really eccentric orbit. You go up and out of the disk and then back down. Well, as you cross through it, think Frogger, okay? You're trying to cross this big thick disk and you're basically going tangentially, you're going across it, and everyone's going to the side, now you're gonna get hit. And just like you got hit before, like a billiard ball, that's gonna make you move in the direction that everyone is already moving. You see? So there's this really strange sort of natural moving together, just shepherding, okay, that happens with the entire disk. And then the nebula assumes the shape of a disk. That's it. So it's not gravity pushing it down, it's not pizza being flung out. This like common motions and collisions that enforce this orderly pattern. Is that weird? You buy it? You have to, but should I explain it better? Yeah. Yeah.
Why is it still not, you know, when to?
Yeah, so good question. So this goes back to like, what is gravity doing, right? So let's go back one, right? So gravity is pulling the material spherically, this part here, not into a flat disk. So Jupiter is big, right? That's why it's mostly spherical. But it also had a disk, stuff that was going around it. And that stuff is in a disk. It's not in a disk. That make sense? The spheres and disks all the way down. And when we see galaxies, not with me, but you'll also see they form this way. So that's the solar nebula theory. Pretty good, right? We're not going to talk about forming the star. That's outside of this class. But you can look around and you can see it. These don't look very interesting to you, but when I explain to you, they will be. Each one of these is a planetary system forming in another part of the galaxy. And what you can see here is in the middle, little bright light, that is the new star. And then the darkness around it is the gas disk that it's forming new planets. So this one, for example, is seen on the edge. So if you imagine that this is the disk, the star would be here, and you're viewing it like that. Let's viewed like that. There's a star. No. Okay, that's this one. And then some of them it's more tilted. So this one is tilted like that towards us. And you can even see this like spider webby thing that's blowing out all the old gas and dust, like we saw in that other picture. And some of these are straight up and down. So here's a really cool one. So you're viewing the disk like this, stars in the middle, and there's gas and dust here. So if you look very carefully, it's dark on the sides. That's being obscured. And then there's light in the middle. See if I can see another one. It's up there, same type of thing. Disk on the side. So we look at all of these. Oh, this one here, right? Disk on the side. That. We look around the galaxy and we see tons of evidence for disks being formed. Okay. And then we look even more closely. What's this? I don't know if you'll know the name of this. I'm just asking what it is. I'd be shocked if you knew the name of it. What?
It's like the thing on the stove.
That's good. I do look at that. It's not that, but it is. It does look like that. Next time I do this with Jade, I'm gonna put like a fake one behind it. Okay, I'll do that for Thursday. Let's see if you remember. What's this one? What does it look like? Looks like a disc. Do we believe it? This is an artist rendition? Like I drew this at home? No, you're not good at drawing. Okay, so this is not an artist rendition. This is a planetary disk. This is called, I think, Fomalhaut. Star is like way in the middle here. Can't see it. And all of this gas and dust is being illuminated by the star. And look at this, these beautiful little rings, right? That made you think of like the stove little coils. What's happening in those rings? What?
Material is getting.
Yeah, going the same direction. The tiers getting clumped together, and that means planets are forming. And every single one of these little spaces, the new planets forming. Cool. Okay. So that explains orderly motions. We're going to continue with the rest of it on Thursday. Any questions? Before we just get into two types of planets? I'll try and find some more exoplanets. We see exoplanets forming these types of planets at large distances all the time. It's sick. Okay. Folks.
Every brain.